Okay, good morning everyone. Thanks for coming along. I can see some bleary eyes in the room. I hope you all successfully submitted and uploaded your design thinking task to Blackboard. If you haven't, please quickly get on that so you don't get penalized too much. Part of the reason I wanted you to submit everything before the lectures is so you can actually pay attention to what we're talking about this time and you don't have that kind of knock-on effect. All right, so we're already in Module 3 out of our 5 lecture modules, so it's going quite fast. Today we'll be talking about is the data fit for use. In the tutorial this afternoon, we'll go through your workbook questions associated with last week's material. And in your practical today, or on Tuesday if you had it, is your first practical associated again with last week's material. Okay, and this is the first practical that has marks associated with it. So make sure you follow what your tutors say in terms of how to submit that. So there's a save and checkpoint thing in your Jupyter notebook. There's also, we'll ask you to upload it to Blackboard, and that's going to be used on a backup in case you manage to do something like delete your whole zone, something awesome like that. So that's what's going on with your practicals. I will take this opportunity to remind everyone that all, apart from the group component, obviously, all of the vast majority of assessment in this course is individual assessment. So feel free to talk to your peers and figure out how did you do that with respect to the practical, that kind of thing. But then you're expected to actually do this yourself, okay? You're not expected to copy and paste pieces of code from people next to you, all right? So discuss with the idea of how to do it, but when it comes to the actual submission, particularly with respect to your practicals, that's individual assessment, okay? And they will be doing plagiarism checks and that sort of stuff, so fair warning. All right, without further ado, I'll hand over to Hina, who'll kick us off for Is My Data Fit for Use?
Okay. Hello, everyone. Good morning. So today we will talk about the third module, which actually relates to the third step of our data science process. Can somebody quickly tell me what's the data science process? Steps 1, 2, 3, 4, 5. Anybody? That was from the first lecture. What's the first step of a data science process? Yeah. Define the problem. That's what you just submitted in today's assignment, right? So the first step of any data science project is to actually define the problem. What do you want to solve? And what's the next step? The next step is getting the data. Third step is my data fit for use, and then we do the modeling, and then we do the visualization. So you should have these 5 steps on your fingertips, okay? So that's the basic knowledge that you should have about data science process. So as last time we discussed that what data do you need? So once you have defined your question, then you need to know that, okay, in order to find the answers, what are different data sources? Are those data sources internal or external? Will you get it for free, or you'll have to buy it? So that the whole process goes around getting the data, right? So once you've got the data, so now we assume the data is in your system. Now the question is this data good enough to answer the questions that you have? What's the quality of this data? Is this data fit for use? So we'll talk about this today. So again, this is just a reminder that where we are actually in the whole process. So today I will talk about data quality, and then Thomas will talk about data exploration and transformation, and then I'll talk a little bit about data enrichment as well. So let's start with this very simple example. This is an example of a table where we've got records representing different articles or documents. So each record has certain attributes. What's the title of the paper maybe or article, which journal it was published in, volume, issue, date, and pages. So we can already see there are some problems with this data, right? So it says the date is misleading. Why? What's misleading about date column?
It looks like year, not date.
Sorry?
It looks like year, not like exact date.
So that there are two problems with the date. One is it's, let's say, inaccurate or incomplete because it only tells you the year and not the month or the day. And misleading, why? What is misleading is the title of that attribute. It says date, but it does not say whether it's the date of publication or is it the date when it was first, accepted. Because sometimes when we, for instance, publish papers, for one date is when it gets accepted, then when it actually gets presented in the conference, and then there's a date when it actually gets published. So we don't know exactly which date it's talking about. So it should be more descriptive. Then there are what's invalid in the pages. What's the problem with the pages column? There are two different formats, so it's inconsistent, right? So the first one says PP and then the range of the pages, and the other one just simply says the range. So it's inconsistent. So the second one might be invalid. And then there is incomplete data. For instance, for the second paper, we don't know the date. So the date is missing. So we can see that this is just two simple records, and there are so many problems. So imagine when you download a data file or a data set, then how many such quality problems you will have. This is another example. Now, this is a very interesting example. This was from one of the a very well-known researcher who presented, I think in 2013 at UK also, he gave this presentation about, he was also talking about, I think, data integration. So here, what's the problem? That this is actually the flight arrival and departure times for the same flights, but from 3 different websites. So there are 3 different websites which are reporting about the same flights. So you can see that all of them are reporting different times. So the arrival time for first 2 is 6:15 p.m. But for the third one, the arrival time is 6:22. So there is a difference of like 7 minutes. Similarly, the departure time is different for all 3 of them. So 9:40, 8:33, 9:54. Now, if you've got data from all 3 sources, what are the challenges here? They are inconsistent, but what's the challenge for you? The challenge for us is which one to trust. Which one is true, right? So there are 3 different versions of the same fact. So which one should we trust? And secondly, if we have to combine this information, then how do we do that? So can anybody guess any reason? They all claim to be true. Like they all say that yes, our information is correct. There's no error in it. So why is there a difference? One good point is they might be reporting in different time zones. So there's a different. So it's clearly 9:40 and 8:30 because there can't be a difference of like 1 hour. So maybe they are reporting from a region which is an hour behind. And what about the arrival time? Why is there a 7-minute difference in the arrival time? Yeah.
One could be the estimated time of travel, the other one could be the actual time of travel.
No, they're both actual arrival times.
Maybe one is reporting the landing time and another is hitting the terminal.
Exactly. Sometimes the airports report arrival time as the moment the plane lands. They consider that's the arrival time, and the other might be when it actually gets to the to the terminal, okay? So that's the arrival. So that might be the reason that there is a few minutes difference. So, so there was another example where data can be inconsistent. So how do we define data quality? So you need to have a standard, so against which you will measure that how good your data is, right? So for different things, we have different quality standards for different, like for a software, you'll have a different quality standard. For a product, you'll have a different quality standard. Similarly, we need to define that what is actually that we are looking for when we say a good quality data or a bad quality data. So it boils down to two facts. The first is that degree to which data can be used for its intended purpose. And that's very important. Same data set can be of a really good quality for one user, and the same data can be of a bad quality for another user, depending upon what they want to do with it. Maybe it's fit for my use. The answers that I'm looking for, it's perfect for that. But for somebody else, that data is not is not good enough to answer those questions. So the quality of the data depends upon how good it is for its intended purpose. And we know that for the same data, there can be various, people can have different purposes, right? So if it's good for you, fine. Maybe I'm happy with some missing values. I don't mind, right? So it works for me. But for other people, maybe even one missing value is not acceptable. Second is degree to which data accurately represent the real world. It's like that the data has to be a representation of the real world scenario. So how accurately it represents, if you start manipulating the data, and if the data is statistically generated and it is not, it does not depict the actual scenarios, right, or actual world, then that's also we say that this is not a good quality data. So dimensions of data quality. So one is completeness. So how many missing values are there? Then accuracy, how accurate those values are. So sometimes maybe, what happens is that just to avoid null values, we try to fill those values with some like statistically generated values, so they might not be accurate. So your data is complete, but accuracy it has reduced. Just like I don't know, Thomas can correct me, if we replace with average, for instance. If we have missing values and we replace with the average of the whole data set, now data is complete, but is it accurate? No, the accuracy will go down, right? Similarly, freshness. Freshness is also very important, that how updated the data is. For example, if you want to make some real-time decisions, you can't make it on something which was recorded 2 days ago. So you have to know what is how fresh the data is. But in some cases, maybe you're working on historical data, then you don't mind if it is just for some tests or some analysis. Maybe I can pick any month's data. I don't mind if it's latest or not. Again, depending upon the use of the data. Consistency again is if the data is consistent. If you're using, again, this is a good example that sometimes we use the whole names and sometimes we use just abbreviations. So if you are reporting a department, if you're using ITE at one place and then you're using information technology and electrical engineering at some other place, it's not consistent, right? When you will run your algorithms on it, the algorithms won't be able to, they'll think that these are two different values. They won't be able to match them. Reliability, again, how reliable your data is. Again, when we saw the last example, 3 different websites, right? So the first is that are they reliable? Maybe they are reporting accurately. So how reliable the sources are from where you got the data. And then there are many more. So these are just for data completeness. We have different standards, different definitions. How can I define my data is complete or not? And then we have, this is again a very important point. This is called a classification of data quality dimensions. There are, we can user independent and user dependent, or we can also call them data centric or user centric dimensions. Now user independent or data centric dimensions of quality are those which are irrespective of the use of the data. So there are certain there are certain quality standards that the data should meet irrespective who is going to use them, right? For example, completeness of mandatory attributes. If anybody has worked with relational databases or you know how it goes, so sometimes there are mandatory attributes, for example, ID. Now you cannot have a record without a student ID. It doesn't matter who is going to use that data later, but if the record is without a student ID, that's invalid, right? You don't know who whether it's a valid record or not. So there are certain mandatory attributes that must be there. Like for instance, if somebody has not provided their phone number, that's okay. That's missing data, but that's all right. You can still somebody can make use of that data. But again, not having maybe your social security number or your ID or another other important attributes, that should be there. Certain level of precision, business rules compliance. If there are certain rules of for example, there are certain rules already defined that these should be, data should not be out of range. For example, again, I always give this example of GPA. Your GPA has to be between 0 and 7. If you're putting it 10 or 12, right, it doesn't matter who's going to use it, but that's not acceptable. So on the left side, we have all those quality attributes which should be met irrespective of the use of the data. And then on the right side, we have the quality attributes which depends upon are user-centric, like the data volume, for instance, is very important. How much, now if I say that I have a small data set, does it mean it's a bad data? And if somebody has a huge volume of data, does that really means that he's got good quality data? So does the volume of data decides the quality of data? It can and it cannot. For some, for example, if I'm doing some, let's say if I'm, I don't know, if I'm modeling, I'm using modeling algorithms and I have to predict, I think more data means that your model will be more accurate. Am I right, Thomas? If it's good quality, but then volume matters, right? So if you took few samples and you just build your model on the basis of them, then your predictions might not be very accurate, right? So sometimes volume matters and sometimes it does not matter. So that's very user dependent or specific. And same is that there's a long list, you can read through that. So good enough is not equal to good data. It actually depends upon its use. Okay, so whose problem is data quality? So obviously, as individuals, if you have downloaded data from somewhere, so that is the time that you will have to live with whatever quality data you've got, and then you will obviously do something to clean it and to make it fit for your use. But when data was created, right, the sources from where you got the data, at those sources, has to be somebody's responsibility to create good quality data, right? So in organizations especially, then whose responsibility? Should it be the responsibility of the management or information technology people, computational problem, or all of above? All of the above. It's everybody's problem, right? Because here we see that okay, so who owns the data? Possession, responsibility, power. Who is liable if data is faulty? Who profits from the data? So actually, in organizations, in government, everywhere, whenever data is involved, there's a lot of politics that goes around it. Because if the data is not of good quality, and if eventually things go wrong, nobody wants to take that responsibility, right? So I remember working for one organization. We were doing risk assessments. We were doing kind of an audit of one of their systems, that whether the system is actually working according to, and all that analysis was to be done through their data. So we got their data, we were running some algorithms and analysis and looking at that, how they have already defined certain quality standards, whether it's matching with them or not. It was so hard to even communicate those results back to them, because everybody said that you cannot directly go and say to somebody that your data was bad. You did not follow the procedures properly. And so it was not hard for me to generate all those visualization, but it was so hard to be so diplomatic when talking to those people and telling them, that, this is how things have gone wrong. And then there were, again, another debate where there was like, whose responsibility was it? At the first place, who were the people responsible for data quality? So this is just talking about that there has to be defined standards and procedures that who will do what. Otherwise, at the end, nobody wants to take the responsibility when things go wrong. So how can we make sure that there's a proper infrastructure for data quality that's called total data quality? So it has 3 different dimensions to it. One is organizational. So there should be some policies and procedures set up at the organizational level that should come from top down. So at the top, management should define that what are our policies and procedures and how important data quality is to us. And then architecture. Obviously, you need some infrastructure, you need some tools and technologies to make sure that the data is collected properly and then formatted and stored. So there are so many different architectures available to do that. And then computational, and then which methods and algorithms you will be using to make sure that. Again, there are so many choices of the algorithms. If your algorithm is faulty, it's not if you use just a simple algorithm, then obviously the quality will be again dictated to that. And if you have really efficient algorithms and latest techniques you're using, so that all comes into the computational part, the people who actually implement those algorithms. Then on top is the technologies and infrastructures, and on top is the policy. Obviously, the whole funding has to come from the top, the management level. What's very, very important is that most of the time people have lots and lots of data, and they think that having all that data means value. Because we've gathered so much data, because we are collecting so much data, it will eventually translate into value or insights and whatever promises the data scientists have made to you. But there is always a gap between the actual value and the perceived value of big data, and that gap is basically because of the data quality. If the quality of data is not good, then you will not get value out of it. This is another example where so poor quality data costs $3 trillion to US government and $611 million to US business for customers' data alone. So again, these facts are so true that 80% of the work goes into data cleaning and working with data quality. So sometimes when your people say that, okay, the data scientist jobs, very fancy words, and they'll have very fancy works to do, and you think about pretty visualizations and graphs and all that. But most of the time, you will be cleaning data. Most of the time, you will be doing what Thomas will talk about. So, this is something that should not be. You should not take it for granted, like that's a simple thing. No, it takes a lot of time and a lot of money goes into it. This is just one example where the chief data scientist, US chief data scientist, he said that on LinkedIn, so there were 4,000 variations of how people could say that they work at IBM. 4,000 different variations. So imagine if somebody was trying to find out how many people work for IBM, it's a nightmare for them. Like, if there's so much variation there. So how can you accelerate the time to value from big data in the presence of data quality problems? So what I have talked about is that once you get the data, that you need to understand that that data will have a lot of data quality problems. You need to understand which problems are the most problematic for you, and then you'll have to obviously solve them. How we solve them to get value is what Thomas will talk about. Okay. Is Thomas running away or what? He doesn't want to talk about it. So, okay. Yeah, that's my last slide. So, so I can talk about data exploration a little bit. That how you find about the problems is through exploring the data. So the first part is you got the data, start exploring it, maybe look at the summary data. What is the sums and averages and means for different columns? How many number of records are in there? And then you can plot some charts. So start with data exploration, and yeah, I'm done.
All right. Yeah. So why don't we all sort of stretch for 1 or 2 minutes, and then I'll start. Okay, can everyone hear me, sort of? Yeah, let's make a start. Good to see people making friends. This is important. Make sure you talk to people at your table. Make sure you sit at different tables each lecture so you get to talk to different people. This is going to be important for forming your groups, making contacts that will be useful for you in your future career. So don't just find your one seat and sit there every single time. Try and, see a few different faces, try and make a few different friends as we go along. All right, and try and pick out who do you get along with, and mark them down for your group project, especially if they have a different skill set or come from a slightly different background to you, because one of the great strengths that you'll be drawing on when it comes to your group project is the diversity of skill set, okay? So you don't want to end up with a group who all have the same background, who all have the same expertise, and as a consequence, all struggle with certain parts of the project, okay? So make sure you're circulating, you know who's in your class, you know who you can get along with, and don't just stick to your one table and your one set of friends. So what I'm going to talk about now is the second of the 4 parts for today's module. That is data exploration. Okay, so data exploration comes effectively through all phases of the data science process. It certainly links in to the data quality phase, as it helps you identify when there might be data quality issues in an I guess, easy or intuitive way without having to look through columns and columns of data, or databases and databases. It also comes through when you're trying to determine, is your data fit for use? Do you actually have the variables that you want? And are they in the format that you need? Are they sufficiently accurate? Do you have enough volume? Are there and a lot of the time, again, you'll be in a situation where people have a whole lot of data, they think they want to answer a particular question, but they have no idea what relationships exactly they might be looking for in order to answer that question. So data exploration is part of the process where you get to dive in or dip maybe your toe into the data and see what sort of relationships, what sort of patterns might exist in the data. And that can feed back and update what the question is, or maybe refine the questioning process again. So I know we have our data science process as quite a linear thing, but really there's lots of feedback loops, lots of iteration through this whole process that happens in reality. Okay. So data exploration is going to be one of those key tools or methodologies that you'll continue to go back to. So what's the point of exploratory data analysis or exploratory data mining? The basic point is to get to grips with the variability that you see in your data. Okay? You're trying to get to grips with variability that you see in your data. So can anyone give me an example as to why, let's say, a column of ages of people in a database won't just be one value? Because continuous, because people have different ages, right? So that's a bit of a no-brainer. That's like, okay, obviously if you're collecting ages of people, there will be variability in the number that you're collecting. The continuous was mentioned, so that again has a bit to do with data quality or data formatting. Are you collecting like the exact birth date, so you could know it down to a day? Are you collecting the time of birth from the birth certificate? Like how much detail do you have, or do you just have their age as a year? So that's sort of a resolution question. But the variability question is, people have different ages. Everyone in this room most likely is not going to be born at exactly the same instant in time, right? What's another example of variability? Can someone give me, although I'm going to point to a table, so can someone at a table give me an example of a variable you might want to collect and what sort of variability you might expect in that? How about this table at the front?
Like grade, mark?
Grades and marks, absolutely, okay, so thinking very student-oriented. So for grades and marks, you'd be very surprised if everyone has exactly the same grade for a particular course, or even the same student has exactly the same grade for all their courses. That would be quite unusual. You'd expect a bit of variability in there. Okay, so we've got variability. Let's take the grades, for example. What might be causing that variability in grades? Okay, what might be a reason for variability in grades? Any ideas here?
Scale.
Scale?
Like, including the maximum, like if you use the point.
Yeah, so there's certainly like an element of scale or resolution, like if we're marking on a 100-point scale, or if we're marking on a GPA scale or that sort of thing, that's absolutely right. But what about, so let's say you know, look at your neighbour. You may or may not get exactly the same grade as your neighbour. What might account for a difference in your grades ultimately?
The amount of time invested in your work.
Amount of time invested in your work. Okay, all right. So the amount of time that you spend studying for the subject, that might be an aggregate variable. So you might already be thinking, I hypothesize there's some sort of relationship between the amount of effort I put in to a course and the ultimate grade that comes out. So try and reformulate that as a data science problem. You might say, so that might be your hypothesis, and then you might want to say, okay, can I get the data in order to explore if this is true, right? Can you somehow get the amount of time that everyone in the class is spending? Can you, at the end of the day, get access to their final grade? Can you build a model? Statistical model that will be able to tell you whether or not the amount of time spent studying might impact on your final grade. I suspect everyone in this room will think, yes, it does, but you know, that's one thing where you think you know the answer, but you might be surprised by what the data tells you. It might not have as much of an effect as you think, especially if you factor in other things like previous experience, right? So experience may have a lot to do with your grade, especially in an introductory course. Certainly an amount of time and effort you put in. Perhaps things like personality traits. Are you more like a perfectionist, or do you just want to get the job done and submit? You know, things like that. So if you imagine you can collect a whole bunch of information, all of these things will be contributing in some way to the variability you see in grade. Okay, so I've broken down sources of variability into a few different categories. So at the top, we've got group or systematic variability. This is quite often what you actually care about. This is the type of variability you care about as a data scientist. You want to be finding relationships between variables. You want to be finding groups that exist in the data. And you want to be trying to find explanations for them. You want to be trying to find, like they'll be telling you something about your data science problem. And they might point you to interesting insights and potential value that you could get out of it. Okay, so the first thing is there's group or systematic variability. Perhaps you notice that there is, in fact, a relationship between amount of effort in the GPA and grade point average that you get. Okay, so what might you want to do as a university management? Encourage students to study more, right? Okay, so that might be a management action. Create some awareness that, hey everyone, studying helps. Another source of variability is natural variability. This is kind of intrinsic variability in the data. And a classic example that comes to my mind is, let's say you look at a tree in the park, right? You look at all the leaves on that tree, right? So let's say you've got a group of leaves that have budded at exactly the same time. They're subject to all the same environmental conditions, and yet they won't have exactly the same length. They won't have exactly the same characteristics. There'll be some natural variability that's associated with the leaves that are growing. Okay, so this is somehow intrinsic randomness that is contributing to your data. Okay, this is unavoidable natural randomness. There's always error in data. Okay, so this comes back partly to data quality, partly it comes to the method of collection of the data in the first place, which feeds into data quality. So this might be imprecision, right? So you might need to know, let's say if you're doing a geospatial thing, you might really need to know the exact latitude and longitude to several decimal places in order for your model to work, or in order for you to actually be able to answer your question, which might be something like, is it likely that power lines are going to be interrupted by tree growth, something like that. But instead, in your data, you might just have, okay, postcode and, aggregate information about trees. What can you do with that? So you could do something, but you can't necessarily do it to the level that you would like. So there's imprecision in the data, there's bias that comes in the data. Imprecision can come in another form as well, particularly if you think in scientific instruments. So you might have a temperature monitor that purportedly measures the actual temperature, but it might be miscalibrated. So there might be a systematic shift, a systematic error, that is just due to the way that you're measuring the thing. Okay, so there are sources of variability that come down to how you're measuring. Bias as well, this is an example we talked about with, particularly with respect to census things. The means or way that you go about collecting data, like telephoning on a landline Wednesday, 10 o'clock in the morning, will inherently bias your sample, okay? So you have to be aware of some of these factors, okay? And then I've put this catch-all bucket, residual variability, which is all other variability out there. All right, so I want to give you guys a chance to discuss, so take 2 minutes in your tables, or swap tables if you feel like it, to think about what might be an example of bias due to sampling that doesn't have anything to do with census collection or surveys, okay? So try and think of a different example of bias due to sampling. All right, so talk away, I'll walk around, and we'll come back in a couple of minutes. Okay, some really interesting discussions happening, and there are a few good ideas floating around the room, I think. So let's just take two examples. I heard a good example from this table.
Frog one. The frog one? The part?
Yeah.
Oh, wanting to know how many frogs are in a park on a given day, or on average, and you only ever go out when it's not raining.
Yep, so that's an excellent thing. So the frogs will not be there when it's not raining, right? So your method of collecting this information will not tell you what you want to know, right? It'll bias towards lower numbers. All right. Does anyone else have an example? You guys?
There's a story from World War II. They were looking at applying armor to planes by looking at where they were shot, but they only looked at the planes that, after they went on a mission and returned, they were looking at the bullet holes inside the surviving planes. Because they only sampled the surviving planes, it created a bias to non-essential damage, I guess.
That is an amazing example, actually. That's an amazing example. So yeah, so if you want to understand, I guess the armoring of vulnerability of airplanes, and you're doing it based on the ones that are shot and return, those aren't really the things that you care about. You care about the ones that were shot and actually went down. All right, so those are two quite different examples of bias due to sampling, right? So even though I might harp on about sort of census and all this sort of thing, bear in mind there's always examples in different domain areas. Okay. So now I'll go a little bit more into, so what do you actually do when you carry out data exploration? So most fundamental information, again I'm thinking about structured data, so rows and columns. Most fundamental thing is to identify what type of data do you have in each of your columns, okay? So what is the variable actually supposed to be measuring, and what is the variable type? Okay, so are you measuring, let's say, age, wage, year, education level, this sort of thing? When you're measuring something to do with it, is it quantitative? So is it a number? Or is it qualitative? Is it a word, a category? And there's also something a little bit in between, which is something called an ordinal thing, which is a category which has an inherent order in it. So I'm not really going to talk about that too much, but those who know, you know. Those who don't, you can Google. All right. So with quantitative data, the fundamental characteristic is it's a number. Okay? The types of quantitative data, you can think about it either being a discrete variable or a continuous variable. Okay? And this, again, there's a little bit of a gray area. So discrete areas, like discrete variables, may be things like age as measured in years, and a continuous variable might be something like time of a sensor measurement. Okay? So both of them have to do with time, in a sense, but one of them you've sort of lumped it into a few particular categories, basically counting. So discrete is often associated with counting things like number of frogs, that kind of thing. Or, I don't know, number of bullet holes, that kind of thing. That would be a discrete variable. Continuous variables tend to be associated with time or space if you've got enough resolution, okay? And again, it's no hard and fast rule. If you have, let's say, the lat-long coordinates, geospatial coordinates, you consider that a continuous variable, but if you've got like a postcode or you've got a suburb or a house address or something like that, you might consider that discrete. All right? So there's no real hard and fast rule on where to draw the line between how you treat a variable, whether you treat it as discrete or continuous. But most of the time, discrete, this is where you've got counting variables, or if it's an aggregate thing, you tend to have a few lumped, how do you say, you're lumping it up rather than looking at it as a continuous variable. Qualitative variables, these are your categories, your labels. Okay, so this is for instance, like whether or not you're taking data 7001, yes, no, okay, that would be a categorical variable. What ethnicity you might identify with, that would be a categorical variable. You've usually got a list. What languages do you speak? That would be a categorical variable, right? So several examples of categorical variables. All right, so I won't go through this in detail, but here's a little example of an HR dataset that you'll be dealing with in your practical too. So there's several columns, as you can see, things from satisfaction level, number of projects they're doing, amount of time they spent, how long they've been at the company in years, whether or not they've left the company, whether or not they were involved in an accident, whether or not they had a promotion in the last 5 years, and what department they're working in, and what salary bracket they have. Okay, so clearly sales and salary are categorical variables, since there are a few categories associated with it. Satisfaction level, last evaluation, these are numbers between 0 and 1, but you'll probably treat it as a continuous variable between 0 and 1. Average hours, this one, it's a count, and you could either treat it as a discrete variable or a continuous variable. Things like time spent at company, since these are all low numbers, you would probably treat it as a discrete variable. Okay. And 0, 1s, so technically they're numerical, so technically they're quantitative and discrete. But if you had y and n, then technically it would be categorical, and you can see there's blurring of the lines. You can turn categorical variables into numerical variables and back again. So there's a bit of a blurring of the lines. Depends a little bit what techniques you want to use, whether they require you to have numbers. Often they do require you to convert categories actually into a numerical value. Right? But fundamentally, these are categorical variables, binary responses. Okay, so I'm going to skip over this one in the interest of time, but a good exercise for you to do is to think about a variable that falls into one of these three categories. Is it a categorical variable? Give an example of categorical variable. Give an example of a discrete variable. Give an example of continuous variable. Have a think about it. Come and talk to me if you're unsure about the terminology. Okay? So, point of exploratory data analysis. There's several points. I have not listed them all here. But often you're trying to search for hypotheses suggested by the data. So that might be a hypothesized relationship between amount of time spent studying and GPA. Often, if you've already got your hypothesis, you have a particular model in mind. You might say, well, I think there's a relationship there. Now I want to test it. I want to build a logistic regression model, something like that for it. So what do you need to do next? You need to check whether the assumptions of your modeling technique are satisfied. And you can do that visually. And you might also use it to support selection of appropriate techniques. And this one is probably going to happen to you at some point, if it hasn't happened already. You might use the results of your exploratory data analysis to inform further data collection. You might realize that you do not have enough data in order to do what you want to do with it, right? So you might say, hello, I actually need ages at more precision than just in their 30s, in their 40s, in their 50s, right? Or you might realize that you need location information at a finer detail. Or you might realize that all of your frog counts come only from one park, and you realize, well, actually what I want to do is understand the health of the Brisbane ecosystem, and if I do that on the basis of just a single park, again, I'll be biasing things geospatially. I won't actually get an overview of what's going on, so I might need more information there. Right, so there's lots of reasons why you might want to do exploratory data analysis. And there's a key distinction between exploratory data analysis, which is basically getting to grips with the data, trying to understand what patterns and variability there are, and confirmatory analysis. So this is when you actually have a hypothesis and a model in mind, and you want to understand or use statistical techniques to test a relationship. Okay? So in conformatory analysis, you might, for instance, split the data into training and test sets, right, to test the validity of the model. I will give you a little bit of a warning, which this picture, I think, sums up nicely. A bit of a warning against completely relying on what the data tells you. Okay? You have to engage your brain at some point in the process. Because if you have enough data and you look for patterns, you will certainly find them. And not all the patterns that you find are going to be sensible, right? So here's a great example. We have two time series. The black lines are number of drownings, so people who died from drowning, pretty macabre. And on the right axis, we've got the number of Nicolas Cage films released. Okay? And there is indeed some kind of correlation between these two things going on. But does that suggest to you the hypothesis that the release of Nicolas Cage films has a link to the number of drownings? Most people would think, well, most people would think maybe not, but you know, so you can get all sorts of nonsense out of it. Here's a little link down the bottom if you want to spend your kind of late brain dead afternoon looking for other hilarious examples of data science gone wrong. So make sure you engage your brain. Don't just find a pattern and say, I found a pattern, hooray, you know, I've justified my existence or my salary. Actually think about what this pattern is purporting to say. What can this actually tell you? This comes down to that oft-repeated line, correlation is not the same thing as causation, right? So just because you've got a pattern in data doesn't mean there's actually a causatory link between these things. You might find something and say, hey, wow, maybe there is, and that's something you or your company might be interested in testing further down the line, all right? But be careful about that. So conformatory analysis, Nan will talk about this in a lot of detail next week. Broadly, there's two categories, supervised learning, unsupervised learning. Key distinction is in what you're trying to do with them. Supervised learning, there's always an output variable you care about. Unsupervised learning, there's no such special variables. Okay? So I've got a bit more detail on the slides, but Nan will take you through that in much more detail next week in Module 4. All right, so finding patterns, visualization is kind of at the heart of exploratory data analysis. You want to produce plots that tell you something that help you get to grips with what's going in the data. There are lots of basic visualization techniques. I'll run through a bit of a laundry list. You'll do this in your practicals as well. Many of you will have seen some or all of these at some time in your past, okay? But it's good to get a refresher, especially if you haven't seen it. So there's lots of basic techniques for visualizing what I call univariate data. So this is basically a single column, right? Visualizing data from a single column, if it's numerical. So things like empirical CDF, histogram box plot, bivariate, quantitative data. So you've got two columns with numbers. You want to visualize or try and see if there's a pattern or a relationship between them. How can you do that? You might do that with time series. So time might be one axis, value might be another, or you might have multiple time series overlaid, like our example before. Scatter plots, which is just plotting the XY coordinate of, let's say, age and height, or height and weight, or something like that together. How do you visualize the relationship between them? Well, you plot a point down on the axis. There are also quantitative techniques, getting basic summary stats out, like the mean, the variance, the interquartile range, the min-max of the data, the quantiles. I'll talk a little bit more about what those things are in a moment. And there are also quantitative techniques that can help you get to grips with a lot of data, dimension reduction techniques, things like principal component analysis, which we don't really talk about, but you may want to investigate for your projects, which might tell you which of the variables in your data set are the most important for explaining the variability that you see. Okay, so empirical CDF, what is it? So remember, we've got one column which has some numbers in them. How does it work? Let's say we've got 100 numbers. What happens is you sort the list, so from smallest number to biggest number, and then you make a little staircase out of it. So you go along on the ground floor, 0, until you reach the smallest number in your data point, then you take a little step up. And that size of the step is 1 divided by the number of data points. Then you go along until you hit your next smallest data point and take a step up. The size is the same, 1 divided by number of data points. And you keep on doing this. Okay, so what this will give you is a graph that starts at the ground floor, 0, ends up at the next floor, 1, and it's taking steps up of the same size all the time, but the placement of the steps is dictated by where the data lies. Okay? So this very first point here is your smallest data point. This very last point is your largest data point. And you can see that there are sort of quite a lot of steps up here in short succession. Quite a lot of so here it's kind of broader. So it's telling you something about the shape, character of your data. All right? One way to visualize it can take a little bit of staring at these plots in order to get familiar with what they are telling you actually about the data. Much more common, which I'm sure many of you will have seen before, is the idea of a histogram. It's very simple. You have, again, numerical data. You divide your axis into boxes, each of the same size, usually. That can be changed, but you basically divide it into boxes somehow, and then you count how many of your data points fall in each of those boxes. And then you draw a vertical line that either counts the total number, or sometimes you normalize this to just be a proportion of the total number. All right? And this again gives you an idea of the distribution of the data. Here, it seems like most of the data is central. Maybe there's a little bit more on this tail, this side, than this side. What's going on here in the middle? We've got these 2 big spikes. Is that real, or is that an artifact of how we've performed the histogram? Okay, so this is something you need to be careful with histograms, putting in default settings. I would say probably this is not a real thing, and it's an artifact of how you've created your histogram. Yeah, question, comment?
Do we use histograms only when our data set has ranges in them?
So when you have like a quantitative continuous variable, then creating a CDF or a histogram makes sense. Okay? Yeah, to try and visualize and understand what's going on there. But I would encourage everyone to play with histograms. Play with what happens when you change the size of these buckets. What happens when you change the number of buckets? How does that change the shape of the histogram? Okay? And probably what you will see when you play around with these things, you can have some data which really only has one little mountain in the middle, can look like it has 2 maybe, just because of the way that these limits of the buckets have been set. Okay, so it takes some time and experience to get to grips with what a histogram is actually telling you. Right? Sometimes something like this, you might suspect there may be a bimodal distribution, like 2 modes, or you might imagine that this might be a single mode, which has just so happens to look like it has 2 modes. And you'll be able to figure that out by playing with it a little bit. All right, box plot. Box plot, again, is kind of a visual summary of some of the important summary statistics that you've got. So this axis is kind of a non-axis. It's a visualization axis. This axis, the y-axis, is the important one. That's the numerical axis of your range. It tells you a few key pieces of information. This solid line in the middle is the median. So half the data is smaller than it, and half the data is larger than it. Okay? Sometimes box plots will also have a line or a circle denoting the mean of the data, which may not be the same thing. That's just the arithmetic average. but always box plots will have a median, which is exactly half the data is bigger, exactly half the data is smaller. Now, how do we draw the size of this box? So the limits of the box itself are what we call the first and the third quartiles. Those are sort of special magical statistical terminology that tell you that the first quartile, quarter, the first 25% of the data is smaller than that. Okay? And the third quartile, the same thing, 3/4 of the data, or 75%, is smaller than it. Okay? So the first and third quartile give you some idea of where is the bulk of the data. Half of your data is lying inside this box. Okay? Exactly half your data lies inside the box. Exactly half is bigger than the central line, exactly half is smaller. Then we have these whiskers. This is a little bit complicated. So you notice we've got these whisker things, and then we've got a few extra dots. So these whiskers are the smallest and largest extent of data points that have not been flagged as potential outliers. What is that? We'll talk about that a little bit later, right? And all of these dots are points which are potential outliers, okay, potential unusual observations. Again, we'll talk a bit later on about how that identification is made by the software, right? But this gives you a pretty good snapshot. You can see already that there's distribution is bulked here. There's a long tail of the distribution going up here, and it's skewed. There's potential outliers as well. So it's quite a useful way to summarize a few key information. Time series plot, again, one axis is just your time variable. The other axis is the value that you've measured. This might be temperature. This might be number of days, something like that. And you can just plot a time series to show you how that variable is evolving over time. Scatter plot, again, as we talked before, this is often when you want to look for relationships between two continuous variables. I've taken a classic example here from Pearson, where he was looking at the relationship between the height of fathers and the height of sons that they had. Okay? So you might imagine there could be some relationship between them, and indeed it sort of looks like there is a relationship. Your next questions might be, okay, precisely what relationship is there? How can I build a model to try and understand this in a bit more detail? That's something that Nan will talk about when he touches on linear regression. Okay. All right. So all of these univariate or one-dimensional pictures tell us something about the shape character of the distribution. There are a few important classifications I want everyone to be aware of. The first one, I've already used this terminology a bit, but the first one is between unimodal and multimodal. What does that mean? So unimodal is when the data essentially is concentrated around a single central peak. Okay? Multimodal is the data is concentrated around several peaks. Okay? So uni, one, multi, more than one. There's also this idea of symmetry, symmetric data versus skewed data. Symmetry, so symmetric data has the same distribution if you flip the axis. Okay? So actually both of these two panels above represent symmetric distributions because they look the same as their mirror image. Right? These two down the bottom, however, if you flip them around, they are kind of mirror images of each other. So these are what we call skewed data sets. Right? They're unimodal, there's one peak, but they're also skewed. And there's lots of terminology floating around. People sometimes call these either positive or negative skewed, or right or left skewed. The terminology that we're going to adopt is right or left skewed, and contrary to popular, or how do you say, your conventional understanding, Right-skewed data, it's the direction the tail points. It's not where the bulk of it is. Okay? So you might imagine right-skewed data, more of the stuff is on the right. Yep, just to be annoying. It's actually opposite that. Right? So right-skewed, it's the direction this little tail of the distribution is pointing in. Left skewed, it's the direction of this tail is pointing in. Yep.
How does multimodal shape character of numerical data affect your analysis?
How does it affect your analysis? So quite often, for instance, for regression, linear regression analysis, one of the fundamental underlying assumptions is that your error distribution, or what happens when you take away your regression line, is actually a symmetric unimodal distribution that has a particular shape, a normal distribution. Okay? And if you have multimodal distribution, it's not that anymore. Your techniques may still work, especially if you try and adopt a robust version of it, but fundamentally, if you have multimodal data in the residuals, you will be violating some of the assumptions needed or required for the statistical techniques. Okay, so it can be quite important when it comes to your analysis if you're selecting a particular technique. It can also be very important because it might tell you something about the underlying character of your distribution. So take this multimodal thing, for instance. You might imagine that this is just the age variable that you've got. What would it mean for there to be 3 peaks like this? Well, there's 3 age groups, 3 distinct age groups in your data set. Okay, and that might tell you, wow, I didn't realize there were 3 distinct age groups of people that I'm dealing with here. Maybe I want to separate them and think about what's, similar or different about these different groups of people. Okay, so it's not always a bad thing. Sometimes, in fact, it's a very helpful thing to identify potential groups that's going on. Okay? All right, so all data sets that you're ever going to deal with, probably in the real world, have missing data. And this is something that is not often dealt with in introductory courses, particularly introductory statistical courses. Most of the time we just assume the data is beautiful, ready to go, and then we talk about our techniques. Reality is not beautiful, it's messy. As Hina said, 80% of your problem is all about data cleaning and getting it fit for use in the first place. So you're going to have missing data, you're going to have null values, you're going to have corrupt values. What can you do with those things? What can you do to treat those things so that you can still perform analysis? So you can still understand and make a conclusion about it. To deal with missing data, fundamentally, we need to understand or have a hypothesis as to why that data is missing in the first place. So you see a null value, you see a missing value. You have to have a bit of insight into the process of data collection to understand how it could be that this value is missing, right? Is your data collected from a call center and things are optional or not, and the person just didn't respond to your question? Is it from a sensor and missing data is telling you something about the sensor? It's broken. Or maybe if it's sensing temperature, maybe it's outside of the operating ranges for that sensor, right? Or maybe the sensor degraded, its battery pack went off, right? So you're going to get missing data, but when you do see it, it's important to understand why it's missing in the first place. So what we're going to do is I'm going to introduce 3 very, very confusing acronyms, okay? These are so confusing that I get confused as well. But I'm going to do it anyway because it's the standard approach to understanding how to describe missing data. And these are called Rubin's 3 missing data mechanisms. The first one is something called missing completely at random. They also will have similar sounding names. The second one is missing at random. Okay, already you can hardly tell the difference between those two. And the third one is missing not at random. And these are 3 very distinct ways in which a value in your data set may become missing. So make a personal exclamation mark or note. You will get confused about this, okay? I guarantee it. So try and keep that in mind when we're going through this next little section. So missing completely at random. What is this missing data mechanism? Effectively, the reason for the value missing has nothing to do with the data or the value itself. It's like you go into the value anywhere in your data set and you just flip a coin with a certain probability. If the coin came up heads, it's missing. If a coin came up tails, it's not missing. If that is a reasonable assumption for why your data is missing, I mean not the coin flip obviously, but that you can treat it as though it's independent of everything else, independent of all the data you have collected, independent of the value, independent of all other data, then we say it's missing completely at random. Okay. So missing completely at random is basically what you would think of as it's just random, right? What remedy can you do? So a very common way which doesn't introduce any bias at all, if you have sufficient data, then you can just perform complete case analysis. So you can just throw out all the rows which have missing data and perform complete case analysis. I say this is a possible remedy because in some situations you'll have so many columns that you're almost guaranteed to have one or two missing data points in every single record. So if you try to do complete case analysis, you might be throwing out all of your data or close to it, right? So when you can do it, complete case analysis works. In practice, especially when you've got large data sets, if you restrict your attention to complete case analysis, you might be going from terabytes of data to just like a few megabytes of data. Okay, so this is one possible remedy. It's not always going to work for you. What is the second mechanism? Missing at random. So this is the one with the confusing name. Missing at random. It's not quite like the previous one. What it says is, well, there's still a coin flip involved, but I'm going to allow the probability of that coin flip to possibly depend on all of the other things I see, okay? So the probability the thing is missing is allowed to depend on all of the other variables that you collect. It's not allowed to depend on variables you haven't collected, and it's also not allowed to depend on the value that you might be trying to collect, okay? So missing at random is still a coin flip, but you might have different coins depending on, but that coin, the probability of that coin is only allowed to depend on all the other observed variables. So this is what we call missing at random. What is an example of missing at random? Okay? What is an example of missing at random? Well, you might imagine, let's say that, again, this is all very approximate, but let's say you ask someone for their LinkedIn profile, something like that, right? So you're going through a big survey and you're asking someone for their LinkedIn profile. And there's nothing, let's just pretend that if someone has their LinkedIn profile, if they have one, they'll tell you about it. So there's nothing sensitive or weird about it. How might the probability of someone telling you their LinkedIn profile depend on all the other things you collect in the survey? Well, one thing, it might depend on their age, if they're collecting it. It might depend on if you ask them whether or not they have a computer or a mobile phone. It might depend on that. But if you have those few variables, then that might be enough for you to determine what the chance is you're going to get a missing value. So that is an example of missing at random. And as you can see from the example, the missingness, the very fact that it's missing, is actually telling you something about the data set itself, right? So the very fact that it's missing might be an indicator that this person may be in a, either extremely young or extremely old, or they might have a technical aversion or be a very private person, right? So this might actually tell you something about the person. Right, so what can we do? If we've got categories, you just add an extra category for missingness. So if you're asking someone for their, let's say, their age or income, and if it's reasonable to expect that if they would just tell you, there's no other reason why they wouldn't tell you, then you can just add an extra category, all right? If it's non-categorical, if it's quantitative, we need to resort to something called imputation, which is the fourth part of today's module, which I'm going super slow on. Okay, so it's the fourth part of today's module, so we'll talk about that a bit later today. Now, missing not at random is basically, it's missing for any other reason, okay? So missing not at random is still, there's a chance that it's missing or present, but the probability, that little coin flip of missing, could depend on the value you're trying to collect itself, or it could depend on some other variables that you haven't collected, okay? So the easiest way to think about missing not at random is when it depends on the value you're trying to collect yourself. And there's a great example, it just comes from, let's say, temperature sensing. You're measuring temperature, you've got a temperature sensor rated between, I don't know, minus 10 degrees Celsius and plus 40 degrees Celsius. And then you shove it on an aeroplane. Then you're measuring temperature on the ground, everything's fine, go up in the air, all of a sudden it's freezing, well below minus 10 degrees, your sensor may be returning null values, right? So the fact that it's missing actually tells you something about the value itself. Or in fact, you can't tell if it's the sensor stopped working or if it's because it was out of bounds or anything else. So dealing with missing data that's missing not at random is actually the most complicated one. We won't really be talking about that at all in this course. The methods that you use to deal with this are typically model-based methods. Sometimes Markov chain Monte Carlo methods as well. Right, so often you'll build a model, a mechanism which encapsulates why this might be missing in order to try and deal with the missing variable itself. Okay, so again, I'll leave this as an exercise for you. This one, really do. I mean, seriously, think down and try and come up with an example of each of the three possible mechanisms. So you've got missing data. Try and really think for an example for each of these cases. That will do a couple of things. It will force you to agonize over the subtle differences between these three things. And it will also get you to imagine why might data become missing in the first place. So I see missing data values in my data set. What are the possible reasons, right? So this is an excellent exercise, but please go through it yourself and definitely talk to me if you're unsure about these things, okay? All right. So unusual data. So often we want to try and identify unusual observations. These can be for several reasons. They might be indicative of a data quality problem. You might have a column that measures someone's height, and it's supposed to be entered in centimeters, and then you've got values like 1.7, right? So that might be telling you someone somewhere in the data entry process has actually entered values that were supposed to be in centimeters in meters instead. Okay, so they can tell you something about data quality. Some things like that you can fix easily with rule-based techniques. Other unusual observations may be due to corrupted sensors. Maybe you've got a temperature sensor that's failing, right? It might be returning wild results. Firstly, you'd like to understand that if collecting temperature is integral to your analysis. So you have to have some way of identifying when is this sensor going out of control. Do I have to go and replace it or ask someone to go and replace the sensor? That kind of thing. So what are they? They're values, numerical values that deviate significantly from your underlying assumptions. They might be errors, they might be natural outliers. Regardless of where they come from, they're probably points that you want to dig a little bit deeper in to try and understand, is this really something unusual that I want to understand something more about? Or is it a kind of true yet unusual observation, and maybe you want to follow up for a different reason? Right? Maybe someone is an exceptionally good athlete. So if we had Usain Bolt or something in this room, we asked everyone to run 100 meters and recorded their time, there would definitely be an outlier, but it would be a natural outlier, right? And you might say, okay, wow, I've identified the next great sprinter. There are also this concept of influential observations, and these are the ones, if you include or exclude, they'll significantly change your model behavior. Typically, classical statistical techniques like linear regression have a kind of double-edged sword. They're very powerful in that they can do a lot if your data is good, but they're also very sensitive. So if there are outliers that aren't supposed to be there, they may change very easily based on these so-called influential observations. Okay, so often your statistical packages will identify what these influential observations are, and you will again want to dig into them and say, okay, let's build a model with the influential observation, without the influential observation, that sort of thing, to try and get to grips with what's really there. The basic error model assumption that underpins all classical statistical work is that once you've built your model, all the rest of the variability follows a bell-shaped curve. It's normally distributed. It has a Gaussian distribution. All of these words mean the same thing, that after you've built your model, right, so after you've taken care of the systematic variability, all of the things you can identify, that's taking care of the modeling process, the remaining variability comes from this bell-shaped distribution. It's normally distributed. Okay? All classical techniques up until around the 50s assumed all this. This is also the basis of outlier detection, those little dots on the box plots we saw before. So for normally distributed data, slightly less than about 1% of data lies outside this range, so the first quartile minus 1.5 times the interquartile range. Interquartile range is just the length of this box, right? The difference between the first and third quartile. So about 1% of probability will lie outside this range. Okay, first quartile minus 1.5 interquartile range, and third quartile plus 1.5 interquartile range. These are usually the defaults set in particular in R in your packages. Some packages might have slightly different defaults, but they use this simple rule and they say, okay, anything that lies outside this range, let's just call it unusual, right? Let's flag it as a potential outlier. Okay? So as a consequence, this rule is often applied to flag potential outliers, in particular for the box plots we saw earlier. So what do you do with them? Talked about this before. Examine them. Are they erroneous? Are they natural? If they're erroneous, what can you do with them? You can replace them by a missing value, right? Or if you can correct them by rules-based methods, then of course you will correct them and they don't become erroneous anymore. If they're natural, you shouldn't be throwing out data. If it's a natural variability, you shouldn't be throwing it out. Instead, you should choose an appropriate technique that's capable of dealing with noisy data. Okay? So the classical things would be to use robust statistical techniques. All right. Okay. So that's takes us to the end of the exploratory data analysis. I think it's probably a good idea for everyone to take a couple of minutes break, go to the bathroom, stretch your legs. We'll get the air conditioner back on, and then when we come back, Hina we'll take the next part, and I will end on talking about imputation. What can you actually do with these missing values? Okay, so let's pause it there, take a walk around, stretch your legs. All right. Let's bring it back.
Okay, so
All right, let's settle down.
yeah.
I know
So
everyone's restless, but we're going to get through this module come hell or high water.
okay. So we talked about data quality, and then we talked about how we can assess data quality, that is through exploration. So you explore your data, you draw some charts, you look at different values, and you identify, how many missing values are there, if the data's got outliers or not. So that's basically the assessment of the quality. We haven't fixed anything yet. So we got the data and we just assessed that, what is the quality of that data. Now the next two parts, data transformation and data enrichment, are basically fixing the problems in the data and bringing it to the level of quality that is required. So we'll talk about data transformation first. Data curation is actually a process which it actually includes a lot of things. It's you can think of it as a process that stays with the throughout the life cycle of the data. So from the point where you actually got the data, and then we clean the data, we get rid of the the data quality problems, and then we create more information about the data, and then we maintain that data. And for example, you've done that exercise once, but next year, more data is updated. If you got more data, and then some metadata about it needs to be updated, and you need to do that. And so it's data curation is not something that you do one time. So it involves a lot of things: data integration, enrichment, imputation, cleaning, all of that stuff involves in data curation. So the word itself comes from, then when you people used to go, and historians, and you dig stuff, right? And when you get something, really maybe 1,000 years ago, you got something out. And then what you do is then you try to label it. What is it? What would be the age of this? Where it belongs? What is it about? So when we get data, sometimes we know where the data is coming from. Sometimes we know what is the schema, what is it about. But sometimes we don't know much about the data, and then we have to actually create that information as well, that what data is all about. For example, look at this process. So we have let's say we have a remote data source. We got data in some XML file, let's see. And it says this, the information is about country, name is United States. Now the information here, when we do the schema discovery. Now schema discovery is basically that we don't know that what is the actually schema of the system, but from the data that we have got, we try to identify that what are different entities in the data, what are the values for those entities, what could be the relationships between the entities. So here we, let's say, identify that the entity is a country, and the current value is, the attribute is name, and the current value is United States. So maybe there's a table called country, and it has different columns, and one of the column is the name, and that name for this particular instance, the value is United States. And then we transform that data into the required format. Maybe I need, or this is stored in XML, and maybe I want to store it in SQL database. Okay, then I create a table called country and columns, and store that data in that way. Maybe I need it just as a text. So whatever format that you need your data to be in, then you transform your data into that format. And then we try to remove the duplicates and linkage, duplicate detection and linkage to external sources. Now, what that actually means is that how your data is related to, if there are multiple sources of the data, how they are related to each other, and if the data is coming from multiple sources, there can be duplicates, right? So maybe the same entity is also recorded somewhere else. So you don't want duplicates in your, for example, if I'm getting data from 3 different sources and all of them have country as a table, then I don't want 3 tables in my my data set, right? So what I need to know, but it's hard to identify that which entities belong to the same, are actually talking about the same thing. So we get rid of the duplicate entities or instances or records, and we link different sources. That also comes in data integration. We'll discuss it later. And then we store the data and metadata. So here sometimes the metadata is with the data, and sometimes you create it for yourself. Then you record that this is the date I got this data from, what was the source, what are the different entities, which version of data is this one. You store it in your internal repository, and then you publish the curated data for different users. If it's an organization, they may give access to the employees or whoever. If it's government collected this data, they might publish it for the public, whoever needs to use that data. So this whole process goes into getting some data, usable before you publish some data. And so all of this includes cleaning, it includes transformation, and it includes integration as well. So data cleaning comes at different levels. For example, schema quality versus data quality, single data set versus multiple data sets, and user dependent versus user independent. So what do we mean by schema quality versus data quality is that what the schema, how many of you know what schema is? How many of you have taken any course in databases? You? Okay. And how many have no idea? How many of you have no idea what? Oh, Thomas. Okay. A schema is basically a conceptual design of your database. So when we say that in the data in a relational database, we store data in form of tables, and each table has rows and columns. So what are different tables? What information will go in those tables in the form of what will be the name of the attributes, types of those attributes, and then how they will be related to each other. For example, I have two tables, department and employee, right? So in department table, I will have name of the department, maybe the manager, who is the manager of the department, etc. And then I have employee, his personal information. What would be the relationship between the two tables, department and employee? Yeah. Sorry? Employee ID, yes, you?
They'd
Yeah.
be a subset of the employees are a subset of the department. All employees would belong to a department.
Yeah, so the relationship in simple terms is that employee belongs to department. That's their relationship. Or the department has employees. So that is the relationship. And that relationship is, if we go to the technical, it will be that there should be an ID with every employee, there will be a department ID, that which department this employee works for. So all this sort of information with all the tables and every table connecting to every other table, there are different types of relationships, that's called the schema. Now sometimes the problem is with the schema itself. For example, there is a missing table. The whole table is missing, or the relationship was wrong, right? There were some relationships missing. So that you need to handle. So that's called schema quality. That whoever designed the conceptual schema is not very efficient, or it is incomplete, or and the things are not relating. How it matters is that exactly if this is a bad schema, that you will have problems running queries on it. And then data quality is the content actually, what is in the tables and what values you have stored. And then again, single data sets, well, multiple data sets. I'll talk about this more when I talk about data integration. And then user dependent versus user independent. Again, it is hard to journalize, again, what I talked about, that for some users, data is clean, other things it's too messy. Depends upon that what kind of, what is the use of that data. For example, the company that I am doing a project right now with them, so I spent like 3-4 months cleaning their data, identifying the actually problems with the data. So I wrote the whole report that, these values are missing, these are erroneous values, these are the outliers and all that. And then we said, let's talk about how we're going to fix it, right? And they said that we don't need to fix it. And like, why? Because we just throw them. They're like, because we collect so much data. They collect data at a minute resolution every day. So they said that there's so much data that even in a day, if 2 or 3 hours are bad, we don't mind. So we can throw, so for them that data is good. Even that data has a lot of missing values, but for their use it's good. So again, it depends upon user dependent or user independent. And then data cleaning in a nutshell, we can do cleaning through rules. That means you already have defined rules, and whichever record or the value does not comply with those rules, that's bad. You need to fix it. Again, the same example that maybe the age need to be within certain range, maybe temperature need to be within certain range. Maybe this is a rule of the university that the GPA has to be between 0 and 7. If somebody is saying 8 or 9 value, that is wrong. So there are already rules defined, what values are valid and which values are not valid. And then cleaning from filter. By filter we means that sometimes we just you just filter the data that okay, for me any data which is older than more than a month is not valid. So if there are values from January 2019, not valid. We just need, so we filter that data. So we put a filter that everything for last 30 days, right? So if you're looking at your maybe transactions, your bank statement, you say last 30, that has filtered the data. So and then cleaning from source. Cleaning from source is that you have one reference or source which you know is accurate data, that is the single source of truth. You compare your data against that. If it matches with that, it's good, otherwise the values are not correct. So there is already some, usually it's very hard in these times that you have such accurate one source of data where you can compare it, but if you've got it a standard, you can always compare it against that standard and clean it from there. There are a lot of tools usually for, again, these doing all these missing values and cleaning through rules and cleaning through source. We don't usually do it manually. There are a lot of tools that help you do that, and one of the tools is this trifecta. There's a small video. I don't want to, due to the time, you can at home you can run it. It's just a 4-minute video which just introduces you to this tool. This is not the only tool. There are many data analytical tools which help you read files into the system, and then you can play around with them. You can use filters. You can choose how you want to deal with the missing values. You can maybe say that delete all the rows with missing values, or replace with the average, or whatever. It allows you to just dice the data, just get the subset of the data and a lot of stuff. So this is just one example. You can look at it at home. And then comes data enrichment. Okay, so what we have talked about so far is basically about maybe a one source of data. Like so you got a data file, right? And you explored it and you assessed its quality, and then you see that there are missing values or there are erroneous values, and then you fixed it. So let's say you fixed it and it's 100% now. It's the best data that you could have downloaded, right? What next? Is it still good enough to answer the questions that you have? The answer is no. Sometimes just one data set or the data from single source is not enough. Sometimes all that you can get from that data is limited information. For example, that the example that Thomas gave about the student, so let's say I downloaded a student GPA or grades file. What it tells me that at the end of each semester, so this is the student, this is the age, this is their discipline, and this is their cumulative GPA. Okay, this is the best quality, no missing values, everything is accurate. There are certain questions that can ask from this data, like what is the average CGPA around this university UQ, or what is the age group, which age group is taking computer science, how many are taking engineering. So there are a lot of summary sort of questions that I can answer from this data set. But what if I want to know that why some students are getting a better GPA than others? Can I answer that from this file? No. What do I need? I need more information. Maybe I need their attendance data, right? Maybe I need some demographic data. Maybe people coming from certain region are doing better than the other students. Maybe what were the degrees they studied before, right? What was their experience and number of hours they've spent? Maybe if they're involved in sports, extracurricular activities, maybe the people who are doing sports, they are spending more time there and don't have enough time to spend there. So there is so much information out there which I have not included. So I cannot answer everything from one source, even if the data is 100%. That's where data enrichment comes. Enrich your data by bringing in other sources of data. So Thomas will talk about imputation and I'll talk about integration, how we combine different data sources.
All right. Okay, so imputation. You've got missing data and you want to calculate statistics on your data. You want to build a model associated with your data. Let's see if this thing is actually doing it. Yes, kind of. Okay, so the fundamental, if you remember nothing else of this lecture, this part of the lecture, the goal isn't to recreate lost data, okay? You're not trying to fill in the blanks. That's not the point of imputation, right? It's a common misconception. So if you remember nothing else, the goal is not to recreate lost data. So the goal is not to recreate missing data. Rather, what we're trying to do is, even though we've got incomplete data, even though we've got missing data, we want to be able to obtain valid conclusions, build valid models that are interpretable in the presence of missing data. Okay, it's not about filling in the blanks. It's about having tools that let you deal with the presence of missing values. So we're only going to discuss, yep, question, comment?
On that basis then, you must have done a test to say what I have got.
Yes, absolutely, absolutely. So this comes from, like, this is after you've made a decision, you say, this is the best quality data that I need. I can't throw out the incomplete cases and just do a complete case analysis. I need to do something with this data which has missing values, right? For whatever reason, you've come to that conclusion. What can you do? All right? What can you do in that situation? Right? We're only going to talk about a couple of this, like any of these topics. You can always go way down the rabbit hole, and there are lots of extremely sophisticated methods to deal with it. We're only going to talk about a couple of the very simplest methods to deal with one-dimensional imputation, and we're only going to talk about it at quite a surface level. So you get a little bit of exposure here in your lectures. You'll get a little bit of exposure next week in the practical associated with this as well. So you get to play around and see what it actually looks like. Okay, so most common thing, you've got a numerical variable and you've got numbers in lots of columns and you've got some missing values in the columns. The first thing you might imagine to do is just say, okay, I'm going to replace the missing value by the average of all the other values. Seems reasonable. What could possibly go wrong, right? So this is bad, okay? Don't ever do this. And I will show you a picture on the next page which hopefully will illustrate why. The reason it's bad is it severely distorts the distribution of the data. What it's doing is essentially creating an extra population that's all concentrated around a particular value. So the actual values we'll be looking at are a big spike, like a big discrete distribution at exactly the mean, and then all the other ones that you've got observations for. It distorts the data itself. It can distort the variability in your estimates. It can increase, can decrease relationships between variables. It can bias estimates other than the mean. So if you care about the variance or something else other than the mean to do with your data, it can bias your estimates as well. And a picture will show you this. Okay, so here is this great book that I've stolen a lot of stuff from, Steph Van Buren. So here she's got, what has she got? She's got some ozone measurement, some solar radiation measurement, 2 quantitative variables. If you just look at one of the quantitative variables, ozone, and think about imputing all of the missing values with a mean, this is exactly what I was talking about before. You're basically having a superposition of 2 distributions, everything concentrated around the mean, and then the real stuff. So you're introducing distortion in your data set. This will affect everything else you do afterwards, all your conclusions. If you think about what happens when you're imputing 2 variables together and you're thinking about the relationship between those variables, what does replacing all the missing values by their mean actually look like? Essentially, you're introducing this cross relationship. Okay? So the same picture, right? But now you're looking from the side. You're looking from the top on here. The ozone will have this concentrated thing around its mean. The solar radiation will have its concentration around its mean. You're introducing this strange cross-shaped 2-dimensional relationship, which is completely artificial, and it's not there at all. Okay? So doing mean imputation and expecting everything to just work is naive. Okay? Don't do this. Even though you Google online, people say, oh yeah, just do complete case analysis, and if that doesn't work, replace it by the mean. Ignore these jokers. They don't know what they're talking about. All right. So you might say, okay, that doesn't work, clearly. What's the next best thing that I could possibly do? Well, we might take a leaf from our sampling book that we looked at before. We might say, okay, I've got a whole bunch of values that are real, and then I've got a whole bunch of missing values. Maybe I'll try a sampling technique. So I might say, okay, let's go along to our first missing value. Let's put all of our actual values in a big bag, and then just reach in uniformly at random, pick out one of the values and plug it in for the missing value, and repeat that process. Okay, so I won't have this same problem of all the data being concentrated on a single point. What does that do? It's a bit better. It's still not great. Why isn't it great? It weakens relationships between variables. Fundamentally, that's the reason why it's not a great thing to do. Okay, I didn't show a picture there, but what you can imagine, I'm just going to do some air sketches here. Let's say you have a 2-dimensional distribution that's long and thin. So all the data you actually have is a long and thin distribution. And you've got a whole bunch of missing data. So in each variable, if you're replacing it, you'll get something that's spread along its whole axis. So all your imputed data will be like in a big circle, right? So you'll have a combination of the actual data, which is a long, thin, strong relationship, and your imputation process will be weakening that relationship by putting a 2-dimensional circle on it. So not a great thing, even in itself.
Sorry, Chris.
Yep.
What does that qualifier mean?
Use only as a first step, you mean? So it means like, well, never recommended for, actual production of results, but if you want to you're trying to implement algorithms and still in the exploratory phase, you still want to understand what's going on, fine, you can just do this as a quick stopgap with in mind that you'll do something more sensible a little bit later on, okay? So the qualifier just means never do this when you're actually doing your analysis. You can do this stuff just for the processes of making your data quote-unquote complete so you can get to grips with it, right? But be aware, you are distorting your data, right? You're distorting your data through this process. The next best thing, right? Again, it's not super recommended, but it's already a step in the right direction. So it's not recommended basically for the same reason that mean imputation is not recommended. So deterministic regression imputation, what does that mean? You've got two-dimensional data, you've got a relationship between these two variables, and instead of the naive replace everything by its mean, what you do is you fit a regression line and then replace all the missing values by their corresponding value on the line. Okay, so you're taking into account the relationship, but again, you're distorting the data in very much the same way as the mean imputation. Here, the distortion is that you're artificially increasing the strength of the relationship. And in a picture, this is what it looks like, right? So in a picture, you've got all of these blue dots are your real data. You fit a straight line through them, and then you fill in your missing data on the straight line. Okay, so it solves, quote unquote, the relationship problem, but it's still got the same issue as the very first approach. You're severely distorting the distribution of your data. So this is not ever recommended to do, again, in practice. So what is a kind of the first minimal, somewhat acceptable solution to this? It's a combination of this and randomness, okay? So what we would like to do is maintain the relationship, but also introduce noise that's commensurate with the noise we see in the data. Okay, so that we would think should be a reasonable thing to do. So that is called stochastic regression imputation. So we fit a regression model, that's our straight line. We fit a model to the noise, and then we replace, we impute values not as the mean, but as the mean plus your estimated noise distribution. All right? I won't be telling you how on earth do I actually do that. There are software packages that do this all for you. But this is the process behind it. I say down the bottom a step in the right direction. Maybe I'm a bit of a perfectionist, but it's still got a few problems, right? It basically, a problem comes down to then the estimated coefficients. So things like your intercept and your slope. It will think that those are more significant, statistically significant, than they actually are. All right, so this does have a minor problem, but it's nowhere near as bad as the previous things. Yeah, question, comment?
How do you get the distribution of noise from non-missing residuals?
So you essentially, so there are lots of ways to do it. So one way is just to let the data speak for itself way. So one is to fit a model, subtract that from the data points, have an empirical distribution, and then do the same draw from the bag of tricks like we had before. That way you don't have to rely on a model. So that's the model agnostic way. The other way is to say, well, I have a very clear idea of the noise distribution. Maybe I know it's normally distributed. And then for every value of your predictor, you might fit a different normal distribution. You might assume it's the same, common variance. It's a very common assumption. And you might fit it based off the residuals. Right? Yep, question, comment? Okay, so let's go back to this picture. So from the blue data points, when a statistician, or at least when this one looks at this data, I see two things. I see a relationship and I see the presence of noise, right? So what we often want to understand is the relationship. That's that straight line thing. But we know there's going to be noise present there. So there is noise inherent in the data. This was our sources of variability discussion right at the start. And what we want to be doing with our imputed data is to essentially try and mimic what the real data is doing, okay? So we approximate this distribution based on the real noise that we see, okay? Does that sort of answer your question? So there is real noise there, and then we're basically saying, okay, I want to copy that as closely as possible and use that to impute my missing values. Okay? All right. Was there another? Yeah?
Is there a line between when you have enough data? Like I'd imagine imputing a small number is a hell of a lot different saying after it's missing.
Yeah, absolutely. Like with a lot of these situations, the answer is it depends, right? So it depends on if you're imputing in a variable that's like unimportant in your ultimate analysis, or if you're imputing on variables that are fundamentally like these are the core variables that you care about. It will depend a lot about the noise that's inherent in your data itself, right? So if you've got data which exhibits a very strong relationship with very little noise, then you can get away with it more missing data rather than the other case where if you've got lots of noisy data, that immutation is just going to miss, you know. So the answer is it depends. It depends not only on the characteristic of the data itself, but it depends on what you're trying to use it for. Okay, so unfortunately, there's no simple answer to that one. Yeah. All right. Yep.
Actually, now there's a thing called that when you say that when you say
Ah, yeah.
means two ways. One is that when the data is enough, it depends that it serves the purpose now. And the second is when data cleaning should be enough because there's so much effort and money goes into it.
Ah, I see.
You don't want to lose the whole cleaning. So, like for example, one technique is that you clean, you build a model, and you check the accuracy of the model. If it's still not up to that accurate, I go back and clean more. And that's a cycle. It's more interactive. That's why in that initial data science process, we said that all the arrows were also going back and forth. So you keep cleaning and building model, going back. You need to clean more. And if your model is accurate enough, maybe you stop.
Yeah.
So that's one of the new things.
That's actually a really excellent point. That's an excellent point. Thank you. All right. So here we go. This thing that we settled on. Just show you the picture, which is the upshot. So your imputed data points are these kind of magenta-y, whatever color they are, and they seem to be following the same distribution. They seem more reasonable. Okay, fine. I will say it's not even the end of the story. I'll give you a glimpse. So the proper way to do it is not to do this once. You have missing data. You don't know the values, right? The proper way to do it is to carry out this imputation, stochastic imputation approach, multiple times. So essentially what you're doing is you're creating multiple synthetic data sets. And then you're building your model and carrying out your analysis on all of those data sets, right? And then synthesizing or combining your results and your conclusions. Okay, so if your model is highly sensitive, it changes a lot from the different data sets, then that tells you something like it tells you something about maybe the data collection side, data cleaning side. Perhaps you actually really do need these things to be cleaned, right? But the proper way is to do stochastic regression and integration multiple times. Again, you're not filling in the data. You're just creating a temporary data set, carrying out your analysis, drawing your conclusions, and then throwing it away, and then getting another one, doing the same thing. Okay, or you can do it in parallel. All right, so we pool our estimates to get our final understanding of the variability in the variance of our estimators. All right, so this is a sort of flow diagram of what that actually does. So this is kind of the, I guess, gold standard of what you want to be doing. Many of you will never actually do this in practice, but you will be now aware of what you can do if you ever had to do it. Okay? Yep.
I assume there's a test as to how many times you should do that.
Yeah, there will be. Even that, I don't know what it's called. So yes, there. As with all rabbit holes, you can go further and further and further and further, right? But here, this is kind of like the best practice, let's call it, for what you should have in mind if you have to work with missing data. You have no option. You've cleaned it the best you can. You've spent all your money there. There's no way for you to get more or better data, or it would be too expensive. What can you do? This is the answer. All right? Okay, so there are other methods for imputation. So one approach, when you've got a lot of missing data, particularly what problems could happen if you're looking at complete cases? So you're throwing out the data throwing out the rows which have missing data. You're keeping only the complete cases. That process might be introducing bias, okay? Because maybe your missing data is more prevalent for some parts of your population rather than others. So what would you have to do in order to correct for that? You have to understand the different weightings you should be applying, okay? Understand who is it that you're getting rid of and how does that relate to the overall population, okay? And there is also several third and fourth year courses you can do on model-based methods where essentially you build a model for the missing data mechanism, you formally encode this missing data mechanism in statistical formalism, and then you use that model-based method in order to help you impute. So you've got a model for the data, you've got a model for the mechanism for the missing data. You can use that model then to impute itself, okay? Usually these methods are iterative, things like expectation or EM algorithm or Markov chain Monte Carlo methods are also increasingly common for carrying this process out. Yep. Yes, effectively. So for missing not at random data, you have essentially no choice but to go for a model-based approach, right? Because the data itself cannot tell you what is not there. You have to build a model which encodes your understanding of the process. You have to introduce something external from the data in order to impute for missing not at random. For missing completely at random and missing at random, what we've talked about is enough. So the data that is there is enough to tell you about the data that's not there, right? Fundamentally, that's the difference. But you have essentially no choice but to go for a model-based method if you have missing not at random data. Okay, so that's the imputation stuff. I'll hand back once again to Hina to tell us about our very final part, and then everyone will be in for a well-deserved stretch of legs and break. All right. Here we go.
Okay, so again, what I said before, that there is a limitation to what you can do with a single data set. Most of the time, to answer interesting questions or the not so obvious questions, we need data from different sources. So this is just a basic definition of what is data integration. And there are different approaches to data integration. So here are just the four main types when it comes to integrating data from different sources. The first one is called data consolidation. Data consolidation basically means when it comes to data, you have to think you should have two views. One is the physical storage of the data, that where does physically data reside. And the second is the control of the data, that who is actually in charge, who is controlling the data. If your data, all your data is stored in a central place and being controlled by a central process, one process responsible for controlling that data, that is more of a data consolidation architecture. So what we do is that, okay, you have got data residing at different places. We bring in all that data, transform it, and store it in one single place. Now, when I say single storage, it does not really mean single machine, right? It can be on multiple machines, but it is being at one servers, or it is controlled by one central application. So basically, physically, we have brought in the data into our system. So can anybody give, so example is already here, data warehousing, for example. So in data warehouses, we collect data from different sources. We transform that data according to whatever format the data is to be stored in, and then we load it into our central system. And from there, it is a unified view for different users, right? So if a company is collecting data from different departments, it's all being loaded into the data warehouse. And from there, whoever wants to run the queries, you can run queries on your data marts, which is a subset of your warehouse, and all sort of analytics can go on that. So that's data consolidation framework. Data federation, on the other hand, is something which is more on demand basis. So the data actually all data is not physically brought in at one time, but when needed, you will bring in that data, you will show some result, you do the analysis, and that's about it. So it's not physically residing at one place, but data is at different places, but those sources have agreed to share their data. So this is more like in a for example, university, we have, let's say we have a student data, there's a separate servers maybe for student data, and then there's some other different, within university there are different departments, they have their own data. And we have not created a central data warehouse, but there are, when needed, you can pull in the data from different departments, and that at that time you can do your analysis and the data can be integrated. Then we have data virtualization. Now, actually data federation is a type of data virtualization. What is virtual? When we talk about data consolidation, that is the actual integration. You actually brought data in and stored it in a central place. When we talk about data virtualization, it is only giving you an it's a virtually integrated. That means that in reality data is not integrated. In reality, it's not at one place, but user is getting a view that all the data is at one place. So if the user want to access the data, they can, so the user will issue a query, and that query will produce the results. How those results got produced, the user is not concerned about that. It will at that time go and collect data from different sources and produce the results. For example, it's easier to give examples from the websites rather than enterprise data and stuff. For example, if you're booking a ticket, you can go directly to the airline website. For example, you can directly go to Qantas or Emirates or any other airline and book the ticket. Or sometimes we just go to maybe Expedia or Skyscanner, these websites. So what do we do there? We put our, where you want to travel, your preferred dates, and then it shows you multiple results of different airlines with the best options. So do you think that the Emirates database is connected to Expedia? Or Qantas has shared all their, no, Emirates database is with Emirates and all the databases are there, but they have agreed to share it when needed. So Expedia goes and extracts that data from their websites. Okay, it extracts the data from their website, and for the user it seems that all of the data was available. To you it will look like that the whole data is down there and you can run queries on top of that. So that is kind of data virtualization, where you get the view that the data is at one place when in reality it is not. And last is data propagation. Data propagation is actually where there is no manual or physical transfer of the data, but the data transfer occurs through applications, and it's event driven. For example, let's assume that there are these oil companies. For example, they have oil rigs, so they have a lot of systems going on the fields, and then they have a central location. For example, Shell, they have office at Brisbane, but their rigs are in Chinchilla and whatever. On a daily basis, data is being transferred from those rigs to the central location, but that data, sometimes that data goes to different applications depending upon what happened there. So they have triggers. If certain event happens on a well, then the data will come here. If some well stopped, the production stopped there, or some well is producing more than what is expected, and for those certain events, then the data will be brought in and the application will do the analysis. That's sort of application driven data integration, right? So the applications are actually transferring the data, or there is a protocols how to transfer data depending upon certain events. So that's another type of data integration. What are different challenges then? So depending upon whether you have physically moved data, or you have moved data on demand, or as a result of certain event, however the data is coming in, once you have data from different sources, combining that data has certain challenges. First, the challenge of schema level, then instance level. Again, schema level, when I say schema level, think about tables, right? What can go wrong if there are different tables? Structural differences and semantic differences. Structural differences is maybe that in one source, the tables have different relationships, or it is stored differently, and in the other source, it's different. For example, in one source, it is normalized. Have you heard of normalized or flat tables? Flat table is all the information is in one table. For example, the information about an employee. So employee number, his age, salary, his personal information, then information of which department it works for, how many children he's got, all this information in one record, okay? What would be the normalized version of this? Split it, make a separate table for department, make a separate table for dependents. So we have employee, his dependents, children information goes in there, department information goes in the department. So we have split it down. So what if one is normalized and the other data set you've got is flat table? Then you'll have to see how you're going to combine that. And then there are semantic differences. Semantic differences is maybe in one source it's called in one data set they have different meaning for they call it department in both data sets, but actually they mean something different. I can't think of a good example. If can anybody think of something like it's called same, name is same, but it means something different. Yeah.
It could be different government agencies or just
Sorry, government agencies?
So it could be a department of something.
Yeah.
So let's say Department of Human Services, but the same word department can be used to name different groups of faculties as well in universities.
Yeah, maybe so department of.
I think when you say course, we mean a subject.
Yeah.
But in many countries, course means a degree.
Yeah, that's also a good example, and the department one was also that. Yeah, so sometimes by course we mean a subject, or just a course, and sometimes a whole course. You know, they're taking a computer science degree also means just a course. So that is where you'll need to know the semantics of the domain that where it's coming from, and then instance level. At the instance level, there will be field linking, how to match same values. Record linking means we need to identify, are we talking about the same record? Usually it's done by some unique identifier. So if it's a social security number, we know that we're talking about the same person in the other data sets too. So we need to link the records. And then entity linking again. If in one table, it's opposite. It's the same thing, but it's called by two different names. So in one data set, they're calling it employee. Other one, they're calling it worker. So basically, they mean the same thing we know as humans that, oh, they're talking about the same thing. But for computers to see that, okay, actually employee and worker tables are same table, not two different tables. So that's basically an entity linking. So the takeaway message from this slide is that data integration can aid in improving quality, but might also hamper. So don't go too excited that, oh, we've got data from so many sources and now the quality will be, data will be really high quality. It can, in fact, introduce some problems which were not there before. So you bring in data to solve some issues, but it can introduce its own issues as well. This example, again, I already talked about it. This basically example shows that there are two different companies, maybe the two companies had a merger, and now they need to combine their databases. So one company is basically, company records are stored in one table, like for example, employee, and the other company is actually stored in many tables. So one is flat file, other is normalized in department, and so when we are integrating it, either we will break the flat file into normalized, or we'll put together all the normalized tables into a flat file. Then when we talk about instance level linking, when we compare that whether it's the same value or no, right? So if you are looking at a name column, and it's in 2 different data sets, and you want to know that whether they're referring to the same name, then again, then there are problems. For example, here look at this. Now this is John Smith, and Mr. J. Smith. So as humans, we can tell that actually it's the same person. It's just that a little different format. So there it is called Mr. J. Smith and O is missing in John Smith, but they are actually the same. But a computer can get confused that they are maybe 3 different people. Similarly, for record linking, look here. So name and address. So it's Jenny Taylor or Jennifer Taylor. Looks like same. Why? Because actually the address is same. So if the same, if 2 records, although the name looks different, but because the address is same, maybe it's the same record. And also, I think there is some difference in the address format. Here it is ST and here it is street. Similarly, when it comes to entity linking, also the problem is that entities, it can be Tiger Woods, Tiger Balm, Indian Tiger. They all represented differently, but might be same, might not be same. So all of these 3 point towards something. What would be the solution to this? A good string matching algorithm, right? So we are actually basically trying to match strings, whether it comes to the name of the tables, entities, or the values, string values, or the records. So this field matching is a mature field now. It's like it started in like 1918, and there's a whole history of these, how these algorithms have developed. We will talk about one of the algorithms, which is called edit distance. Very simple algorithm, and that's why it doesn't work most of the times, but we will discuss it because it's so simple. So edit distance says that a classical string matching algorithms actually fail if there are such small differences. Just like I said that John and JHN, because O is missing, a simple string matching algorithm will say that it's not a match because it matches each and every letter. This added distance actually say that rather than comparing exact matches, we should look for close match, that how close one string is to the other string. If they are nearly similar, then we should take it as a match. Now when we say nearly similar, if we say that how close it is to the other string, then that means that we need to define a distance between the 2 strings. So if you define distance between 2 strings, then you can say that the strings whose distance is maybe less than 1 or less than 2, they are a match. And if the distance is more than that, we consider them as 2 different strings. So edit distance basically defines the distance between 2 strings as the number of operations it will take to convert one string into another. So if it is from John to John, how many operations I need? So I take this one, I take first string, and I try to convert it into the second string. And the operations are insert, delete, or replace. Right? How many letters I need to add or delete from John to make it John? Just 1. So if I take H out, it will be John. Similarly, in second one, if I take O out, 1 operation. And in the third one, how many operations? 2. I think I have to take H out, and then I have to insert S, and I have to take N out, or maybe replace N with H. If you use 1 delete and 1 replace, it will be 2. If you are using 2 delete and 1 insert, it will be 3. Depends which operations you are using. So in that case, that's how we can compare different strings, and we can see that if they are close enough. Yeah, so simple task. Can you tell me what would be the edit distance of shoe and show?
1.
Okay, 1. And broad and brand? 4? Delete and replace. So we'll have to first take out O, delete O, that's 1 operation, and then insert A, and then replace A with N. Sorry. Yeah?
The number of operations, and then the concept of minimal edit distance. Like, what's the smallest number of operations?
Ah, okay.
I think you're asking for minimal. So
Yeah.
the minimal one would be delete the O and insert an N.
Delete O and insert? Okay. Okay, thank you. Yeah, so there is, it can be 4, it can be 3, depending which operation you choose, but the final added distance would be the minimum. What were the minimum number of operations needed? So like if it can be done with 2 operations, we don't need to do it with 4 operations. Okay, thank you. And then again, kitten and sitting. 3. We replace K with S. And we have, yes, I and N and G. I and G, so 3, basically. Okay. So what's the problem with the edit distance? So actually the problem with edit distance is that the 2 strings are considered similar if their distance is less. And so it may be a costly operation for large strings. So if you have a large text, then, even it's a computation by the computer, right? Adding, deleting, and, finding the minimum distance. So the computation in itself can be costly. But more than that, the issue is that it is good for finding typos, right? So if there is a typing error, you missed one letter somewhere, it will be very good to pick up on the typing errors. But for entity matching and for actually seeing whether these names are the same or that the 2 entities are the same, sometimes what happens is that without any context knowledge, without any domain knowledge, what it will do is that it will make mistakes. For example, this is a very good example that here if we are looking at the company names, then AT&T Corporation versus AT&T Corp. Now the added distance of AT&T Corporation and AT&T Corp will be large, because it's corporation and corp when you try to convert that, but we know that it's actually the same company. At one point they're just using an abbreviation, and on the other hand they are just using the full word. On the other hand, it will say that IBM Corporation and AT&T Corporation are the same. Why? Because IBM 3 letters and AT&T 3 letters, it will replace it. So its added distance is less than the added distance of the first one. But in reality, first one is a match and the second one is not a match. So if we already had some context that, okay, the company's name use abbreviations, or, corporation and corp maybe is the same thing, then it might not have made that mistake. Similarly, it can only work for text values, not for numerical values. So if you're storing values as strings, so we know that 500 and 499 are very close because there's just a difference of one here. But if you look at it as a string, then all 3 letters are different, 500 and 499, all, it will say that they are different. But it will say that 500 is same as 800 because both have two zeros in it. So it will only need to replace 5 by 8. So, but there are many variations and refinements which work, and maybe if you take this Info 7907 course, you might know about them. And then, this is just a repeat. Okay, so in the end, data integration and data management is again a very mature field. As in the first lecture, Shazia talked about that, that whole database management, it has evolved for last 40 years or more than that. And when long before we had data science and all that, we had distributed data systems. We were working with distributed data system and data integration. So all of it is a mature field. There are tools out there, there are algorithms out there. What's challenging is that doing all of this in the big data era. So integration was all good, right? So we had tools and algorithms, but now all those tools and algorithms are failing when it comes to big data. One is the quantity of the data, and the other important thing is that now there is so much unstructured data out there, and most of the time we don't have any knowledge of the schema. We don't have any knowledge of the metadata, and without knowing what data is all about, then combining it, it's very hard. So before, in the distributed data systems, everything was defined and structured. We knew that it is physically located on different places, schema is different, but we know the schema. We know the schema of data set 1, we know the schema of data set 2. It's only a matter of combining it, right? So we develop algorithms for that. But what if you don't even know the schema? You don't even know when it was created, for what purpose this data was created. For example, if you give me this the design thinking task that you have done, what was the data coming from? Sorry?
Citizen science.
Yeah. The citizen scientist. So if you give me a data file, I won't be able to make any sense of it. Because I won't know what, sometimes even the terminologies you don't understand, right? Even when I started with this smart meter data, and it took me a while to understand the terminologies, you know, what does grid means and voltages and impedance and all that. I'm not an electrical engineer, I'm from computer science. So if, you know, the data scientists are not the domain experts. So if you have to combine data coming from so many different sources without any information about data, so that these are the biggest challenges that for data integration in the era of big data. So be aware of all this when you're working and when you're combining data, and also combine as much as you need. That's very important. Sometimes students define their projects and they say, oh, we will get data from here and here and there. We will also put this question into it. We'll try to answer this also. And then they struggle with, managing all the data. So sometimes small and simple is enough. Depends how you're going to use it. That's all for today.
Yeah. Reminder, we have a tutorial at 2 o'clock, so that's where we'll go through the workbook questions on the material from last week. So I'll be there at the tutorial at 2 o'clock. Come along. If you have a chance to look at it before then, that would be great. But otherwise, just stretch your legs, have a late lunch, enjoy yourselves. So do I.
Hi, Thomas. Okay.